Sure, it would be better if you keep it in the morning itself.
What, sir? What is the timing for quiz? Quiz, I think in the evening after 6:15. After 6, you can say, not 6:15, but after 6. So presentation not visible because I have not shared till now. So morning, right? Means 10 to 11.
Yes, sir, that's fine.
That will, okay, okay. So let us move. So today we will see what will happen for the non-ideal case. Okay, so in case of non-ideal, so till now we have seen the capacitor is. So what is the lecture number 7, right? Lecture number 7, and today's date is okay. Let us talk about the non-ideal case, that is non-ideal, where the phi m is not equal to the phi of s. So it means that phi of m minus phi of s is less than 0. So where phi m is the work function for metal and phi of s is the work function for semiconductor. So here we can relate that phi m is less than the phi of s. So it means that the work function for metal should be less than the work function for semiconductor, right? Okay. So now what will happen in that case? We have to check what will the band diagram now. So it will be flat or it will be tilted. Can you guess?
So tilted.
Tilted, right? Because here the work function for the metal is quite less than the semiconductor. So at the metal side, it will be quite less. So let us draw the energy band diagram. So let us say this is like tilted here. So the energy Fermi level for the inner metal side is represented by EFM. This is metal, this is oxide, and here this is the semiconductor, right? So now, so the in a vacuum also it will be tilted, the energy of the vacuum, and it will be like that. So this is the E vacuum, and the direction of the electric field will be like that. Okay, so now we have to draw the, okay, so let us talk. This is, let us say this is EFS. So if you compare, see here, this is, let us say Q phi m, and so here it will be, okay, so this will be EFI, right? Or EFI, you can say this is EC and this is EV. So here automatically whenever the phi m if is less than phi of s, that is in a non-ideal case, there will be a band bending here, right? So if because of the band bending, the band diagram will look like that. So if you see, this is the q into phi of s. So this region is, because of the non-ideal case, there will be a charge here. So it will be negative charge, there will be positive charge. So what will happen if you want a flat band, then you will have to apply the negative bias. If you want the flat band, so here there is a band bending, right? because of the non-ideal case, and there are several reasons for the non-ideal case, I will let you know. So here there will be a band bending. So want if you want flat band, then in that case what we will have to do, that we will have to apply some potential here. So because of that potential, you will get the flat band. So the problem is that which type of uh, mm, voltage we can apply here.
Negative voltage.
Negative, right? Because we know very well, in case of negative, if you remember, in case of ideal case, the band bending was like that, right? If you remember. So this is EV, this is EI, and this is EC, right? If you remember. So if you want the flat band for this case, then you will have to apply the negative voltage, that is V less than 0. So here we will have to apply V less than 0. So in that case, you will get the flat band, that is so like that, metal, oxide, and semiconductor. This is EV, EI, and EC. So now, if you what is the characteristics, CV characteristics? Anyone can remember? So the CV characteristics was like that. If you see on the x-axis, we are varying the voltage, right? So this is the voltage. Let us say this is plus voltage, this is minus voltage, and here on the y-axis, capacitance. Okay. So if you remember, at V is equal to 0, what is the value of capacitance?
CI.
CI, right? So CI means that, and for C less than 0, for the ideal case, let us talk about the ideal case. So it was constant, right? For V less than 0. And after that, what is happening? It will decrease up to the voltage V is equal to VTH, right?
VTH.
After that, again, it will become constant at high frequency. High frequency. But due to the non-ideal case, what will happen? Let me change the color. Okay, so this is for the ideal case first. Ideal case means that phi m should be equal to phi of s. Now, in case of what will happen in the case of non-ideal case, we have to see, because of the non-ideal case and difference in the work function, the capacitance will look like that. Okay. So this change is due to the non-ideal. So there are several reasons. Phi m is less than phi of s. This is the first case for the non-ideal case. Second case, okay, let us discuss about it here. So here, first of all, since we are talking about the interface, if you see here the circuit, this is metal, oxide, and semiconductor. So this region is the interface. This is the interface. So let us see, this is the interface, is known as metal oxide interface. And this interface will known as oxide semiconductor, or you can say insulator semiconductor, right? Semiconductor. So we are not considering any defect at the interface. Just only we are considering the case first, that is phi m is less than phi of s. So here we are not considering not considering any defects in the oxide layer and no trap or defects or defects in the semiconductor. So I will let you know what are the major reasons for the defect. Have you heard about the term lattice constant in semiconductor?
Sir, do you mean lattice structure?
Yes, lattice structure.
Yes, sir.
So what do you mean by the lattice structure? Can you give me a brief introduction so that I can explain
Sir,
about the
it
defect?
sir it tells about different orientation in a cube.
Yes. So for every semiconductor material, it has different lattice constant or lattice structure, you can say. So let us say here we are using the three material, right? Metal, oxide, and semiconductor. So whenever we combine different types of materials together or sandwich like a structure, you can say, then there will be a defect due to the lattice mismatch. Because let us talk about the semiconductor, let us say the silicon. Silicon has its own lattice constant, oxide layer has its own lattice constant, and metal has its own lattice constant. So there will be a difference in the lattice constant due to which defect may arise at the interface, or you can say in the at the heterojunction. So because of that, the capacitance may also change. So now let us talk about the next case, that is the interface defects. Interface defects. Interface defects may change the CV curves. So where will be the interface? Let us say this is the metal, oxide, and semiconductor. So the interface will be between metal and oxide, and also the interface will be between oxide and semiconductor. So here, at this region, there will be interface defects. So because of that, the semiconductor CV characteristics may affect it. As a result, you will get some different value of capacitance with respect to the voltage. So this is all about the non-ideal case. Now we will move to the another topic, that is MOS device characteristics. So here, let us focus on the MOS device characteristics. We focused here so that we can also we will also solve numericals based on this topic, MOS device characteristics. So let us discuss MOS transistor, or you can say MOSFET. Capacitances. So based on the above topic, we will see here. So let us first draw the structure. So here I will try to draw the 3D structure, but my drawing is very weak. So let us draw. Okay. So, okay. Okay. Good. So let us see. We are talking about the N type MOSFET. So it means that the source and drain will be N plus doping, and here it will be P type. And the length between and the distance between drain and source is known as channel length. Okay, which is represented by L. Okay, so here, if you remember, so this part is known as, and this one is, let us say this is source, right? And this terminal is known as gate, and this one is known as drain. Okay, and this is the thickness of the oxide layer. This is oxide layer, that is SiO2. So this oxide layer is, the thickness of the oxide layer is Tox. Okay, and this is known as width. So we have to remember this term. So let us draw the 2D diagram also. This is a 3D representation of the device. Now we will draw the 2D. This is 3D. Okay, so let us draw P type, and here the length is represented by L. So this thickness is represented by Tox, that is the oxide layer thickness, and there will be a metallic contact here, that is gate, source, and this terminal is drain. Okay, so now let us talk about the first capacitance, which is, there are various types of capacitance under the MOSFET transistor. The first capacitance is known as the oxide capacitance. So focused here, oxide capacitance is represented by COX. Okay, and its unit is, always remember, its unit is farad per centimeter. Okay, so COX, that is, we know very well of any insulator. So what will be the value? It is just the permittivity of that oxide layer divided by the thickness of that oxide layer. So this is the definition of oxide capacitance. Now we have to discuss second capacitance, that is second, there are two types, that is gate to body, which is represented by CGB, and second one is known as gate to channel, gate to channel capacitance. Channel, which is represented by CGC. Okay, so here to the structure we can realize gate. This is the gate, right? So at the gate we are using the metal oxide layer, and this is the body. This is known as the body. So under no bias, if you will not provide any biasing, then which type of charges will be here? Which type of, what will be the type of the carriers in this region?
Immobile.
E-mobiles? E-mobiles are just only the P-type, holes will be there. There will be a holes, right? Because we are not providing any bias. Okay, so there are three conditions, if you remember, that is three region of operations. So what are the three region of operations?
Cut-off linear saturation.
Okay. Three region of operations are cut-off, linear, which is, okay, linear, and saturation. Right? So these are the three regions of operations. So here I mean to say that here we need to find the capacitance under these three regions. So okay, so let us talk about the first capacitance, that is gate to body capacitance. So let us talk about the 2A, that is gate to body capacitance, which is represented by CGB. So here gate to body, so under three category, right? So we are interested in finding, let us say gate to body. It's okay. So the conditions will be cutoff, linear, and saturation. Also, we know what is the conditions for cutoff? Voltage
VGS
range,
less than VTH.
V
and
less
VGS
than 0, right? Okay. Linear, V greater than
Greater than 0.
greater than VTH, right? But the condition will be,
Oh, sorry. Yes, sir.
yes, VGS should be greater than VDS
Plus
minus,
VTH.
plus or minus.
It's a plus.
Okay. And here also the V is greater than VTH, right? And the condition will be VDS now will be greater than VGS minus VTH, right? This is the condition. So now we are interested in
Sir,
finding.
for cutoff, it should be VGS should be less than VTH.
And
No,
drain current zero.
cutoff means similarly V is less than 0, V is less than VTH, you can say, right?
Yeah, yeah.
Okay, okay. So here let us say this is, okay. So it is VTH, right? Okay. So now we are interested in finding gate to body capacitance. So there are three conditions. Okay. So now we have to understand under these three conditions cutoff. V is less than VTH. Okay. So when the V is less than VTH, it means that there will be a holes here, or you can say immobile ions here, right? Positive or negative. Which type of ions will be here? V is less than VTH, it means that still the voltage is greater than 0, right? So still voltage is greater than 0. It means that positive charge will be here, means here. And what about the charges are here?
Sir, negative immobile ion.
But it is not greater than VTH, right? So there will be a depletion region here. So it means that still you will get the capacitance, that is the same capacitance, because there is no formation of there is no formation of channels here. If V is not greater than VTH, it means that there will be no channel here, right? Only depletion region will be there. That is true?
Yes, sir.
Okay, so it means that the same capacitance you will get as for the oxide capacitance. The only difference will be here that COX, right? But COX is capacitance, means farad per centimeter square. But here we have to find the capacitance, the unit should be farad. So if you want to convert farad per centimeter square into farad, then what you will have to do that? We will have to multiply it by this by area, right? That is true. We are interested in finding the capacitance in farad. Only you can find the oxide capacitance in farad per centimeter square. However, the remaining capacitance, that is gate to body or gate to channel, you will have to find the capacitance in terms of farad only. So under cutoff region, the same capacitance you will get, that is depletion capacitance, that is oxide capacitance, but you will have to multiply by the area. So what is the area here. Anyone can guess what is the area here? What is the definition of area? Area is equal to length into
Width.
width. So here the area, the length is L, right? And width is W. So this capacitance COX will be multiplied by W and L. What about the linear region? Get to body. In the linear region, what will be the value of get to body capacitance? Under linear region, what will happen? There will be a channel, right? N-type channel will be here. So the N-type channel will be here. So it means that there will be no contact of this get terminal to the body because channel has been formed. So it means that the capacitance will be 0 here because of the isolations. So similarly for the saturation, 0. Any doubt? Because we are talking about here the term that is gate to body. So where is gate? Gate is on the top. Gate is on the top and body is here. So under linear region, what is happening? The channel has been formed. N-type channel has been formed. So there is no contact of gate to the body. As a result, gate to body capacitance will be 0 under the linear region and as well as in the saturation region. Any difficulty? Yes? Okay, so now move to the gate to channel. So under gate to channel, what will happen? In that case, so now we will move to the gate to channel 2B, that is gate to channel. Get to channel, that is GC capacitance. So if you see gate to channel, right, we are interested in finding the gate to channel. So when the channel will be formed, under which region of operation?
Linear and saturation.
Linear and saturation, right? So we know very well, and in the linear region, the channel is symmetric, right? Means the length or width of the channel is symmetric for the drain and source side. So here, if you see, it means that gate to channel. So gate to channel means gate to drain side. Here there will be two capacitance. Gate to. So just write here gate to so channel, which will be equal to the summation of gate to drain plus gate to source. Why it is in series like that? Why it is look like that? Because if you see that circuit diagram here or the device structure, both the capacitance are connected in parallel. So we know the rule of capacitance whenever they are connected in series and parallel. How can we find the equivalent, right? So the equivalent the capacitance of parallel connection will be simply addition. So now in the linear region we have to check. Okay, so let us talk about there are two capacitance here, gate to drain and gate to source. So let us see about the gate to channel. So again here it will be the three regions, that is cutoff, linear and saturation. Okay, so there are two types, there are two capacitance under this, that is gate to source and gate to drain. Okay, so let us talk about this capacitance. So gate to source, if you talk about the gate to source or just talk about the gate to channel first. So gate to channel. So what will happen in case of cutoff region? What will be the value of gate
0.
to 0, right? Because there is no channel formed under cutoff region. So the value of gate to drain, or and you can say gate to source capacitance will be 0 under cutoff. That is very good. So it will be 0. What about the linear region? If you talk about the linear region, then what will be the value of gate to drain and gate to source capacitance? Again, you have to take the oxide capacitance here, right? So see here, the oxide capacitance multiplied by area means W into L. So since the length through from the source to drain is symmetric, it means that just we have to divide the capacitance by 2 or half, you can say, right? So if you will divide by 2, just you have to divide by 2. Now we have to check for the saturation. This is a very good topic here, saturation. So just I am going to draw the channel length first of all. So this is the channel under saturation. Under saturation. So after observing this graph or this device structure, what can you conclude for the gate to drain capacitance under saturation?
0.
Yeah, exactly. It will be 0. Very good. It will be 0. So gate to drain capacitance under saturation is 0. What about the gate to source?
Oxide capacity.
Yeah, oxide capacitance, but half or more than half or less than half. What can you predict from here?
They're full.
Full, no full.
Sir, half.
Yes, not exactly half, not exactly full, because practically it has been proved that it is slightly greater than half. So slightly greater than half, so it has been practically proved that it is nearly 2 by 3 COX W into L. So now if we talk about the gate to channel, so we know it is the addition, right, of above 2 capacitance. So what is the value of gate to channel capacitance under cutoff? Under cutoff, yes, it will be 0. What about the linear region? Under linear region, it will be just addition of the above 2, because GC is equal to, if you see the equations, GC is equal to CGD plus CGS. So if you will add these two capacitance, then you will get COX W into L. What about the saturation region? Simply you have to add, then you will get 2 by 3 COX WL. So here you can see that these two capacitance, I mean CGS and CD, or you can this one, this is the bias dependent. Bias dependent. Okay. Now one more thing we have to observe here, that whenever we drawing the structure, here you can see there is no overlapping of the oxide layer with the drain side and the source side, right? There is no overlapping. So this is the ideal case. What will happen if there will be overlapping of the oxide layer with the drain side, to the drain side and source side? So let us draw the structure once again, so you can understand. So that capacitance, actually third capacitance, is known as the parasitic capacitance. Parasitic capacitance, or you can see overlapping capacitance. So let us draw the structure first, then we can conclude here. So the structure will be like that. So during the etching of the device, there will be overlapping, because we cannot exactly remove the SiO2 from the top of the device, P-type. n plus, and here, because initially we always implement the SiO2 layer on the top of the device. After that, we etching, and then we form the oxide layer for the gate layer. This is SiO2. So here, this is the metallic contact, that is gate, drain, and source. So here, let me change the color. So here you can see this region is the overlapping here. Overlapping. Here also you can observe this part is overlapping. So again, let us say the length of this overlapping is, let us say, L0. Okay. So here again there will be two capacitance, that is get to source overlapping. So overlapping. So this is capacitance is represented by C, get to source overlapping, and another is the get to drain overlapping. So because of that, the parasitic capacitance is known as CGD overlapping. So if you know the length of this overlapping, then the capacitance will be, what will be the value of capacitance? Simply it will be COX, because oxide layer is overlapping, right? So we know the capacitance of the oxide layer, that is COX. So what will be the area here? It will be simply L0 multiplied by width, because width will remain same. If you see the 3D structure, if let us say here it will be a overlapping, then width will remain same. Width is not going to change. So, and this one will be equal to same, that is COX L0 W. So what you have to find a difference where L0 is the overlapping length. Overlapping length. So now you have to observe that this parasitic capacitance is independent of biasing. Independent of biasing. However, one important point, however, what will happen? However, if you are interested in find the total get to source capacitance, that is CGS, which will be equal to, so the result will CGS plus CGS overlapping. So we know very well this one is the biasing dependent, right? Biasing dependent. And this one is independent, bias independent. Bias independent. So what do you think about the overall gate to source capacitance? It will be bias dependent or bias independent?
So dependent.
Yes, the overall gate to source capacitance will be bias dependent in that case, bias dependent. Similarly, for overall gate to drain capacitance will be equal to CGD plus CGD over length. So overall, you can say this is the bias dependent. because of the one parameter is one capacitance is bias dependent and another one is independent. But still, if you combine the both, then you will get overall capacitance will be bias dependent. Now, the fourth type of capacitance is known as the depletion capacitance. Depletion capacitance. So which is represented by GD. So which is also bias independent. So if I ask you from the total capacitance, which one is not bias dependent, means which one is independent, which one is bias independent from the above all four capacitances. So your answer will be parasitic capacitance are the bias independent and also the oxide capacitance. So now let us talk about the depletion capacitance. So depletion capacitance, let us draw the structure once again. So here this is p-type material and this is N plus and this is N plus, and here let us say this is the oxide layer, and on the top of the device this is gate, drain, sorry, so okay, drain source symmetric, no problem. So source you can see. So now this is N plus material, right? N plus doping, and this is p-type doping. So what will happen at this region? Can you guess what will happen to this region?
Depletion region would be.
Depletion region, right? Yes, there will be a depletion region. So because of that, since the device is symmetrical, this will be a depletion region. So to find out the depletion capacitance, we must know the value of this is a depletion layer. So to find out the depletion capacitance, we must know the value of junction capacitance, right? Depletion layer. So to find out, the most important parameter is to find out CD. We must know the junction capacitance, that is Cj, and its unit is given by farad per centimeter square. So Cj you can calculate by F7S by XD. I will let you know what is XD. So X7S is the permittivity of this bulk material. Okay, so now we have to see what is XD here. So let us see. Let us say that the thickness of this depletion layer is XD. Okay. Okay. So here, if you see the thickness of this layer, the depletion layer is XD, and you know the material properties, that is relative permittivity of the semiconductor material is F7S, then you can simply calculate the junction capacitance in farad per centimeter square. Now, we are interested in finding the depletion capacitance. So here, there are two types of depletion capacitance. If you see, the first depletion capacitance will be source to body and drain to body, right? So since this is symmetrical, so we will calculate just one and then you can calculate. So let us say for the symmetric device, this will be equal. So first, let us say symmetric, under symmetric. So let us say talk about the source to body. So source to body. So let us say the width or length of this material of this n-type region is, let's say this is m, and this height is given by n. Okay. So if we divide, if you see, let us say this capacitance is bottom capacitance, because here if you see the depletion layer, so depletion layer is all around the three sides, right? Three sides means one capacitance will be at the bottom side and two capacitance will be on the left hand side and right hand side. That is true. Means through the side wall, because here is also the depletion layer, here also depletion layer, here also depletion layer, and if we are assuming the similar height or of this, or you can say depth of the depletion layer, that is everywhere it is xd xd xd, we are assuming here. So what can you assume here? C, your source to body, which is equal to C bottom plus 2 twice the capacitance of the side walls. So as I told you, to calculate the depletion capacitance, we must know the junction capacitance, right? So here junction capacitance. Okay. So junction, the unit of the junction capacitance is farad per centimeter square. So, but we want to calculate the source to body capacitance in farad. So we will have to multiply this term by the area. So for the bottom capacitance, what will be the area? Can you guess?
into XD.
Not m into xd. Xd is the thickness. Oh, okay. If you see the 3D structure,
MW.
see here. Yes, yes. So let us see the 3D structure. Here we are interested. This one. This, let us say this is m. And if I ask you to find out the area of this n plus region from the bottom line, bottom region, then what will be the area? M into W? Right? So M into W. It is M W plus 2 C sides. So let us say G, Cj. So what about the area of for the side walls? Yes. What will be the cross sectional area for the ends for side wall?
NW.
NW. It's very important to understand. Okay. So similarly, for the get to drain to body, capacitance will be similarly. But this is all about the linear region I told you. Right. So what will happen in case of the saturation region? Can you guess?
Sir, asymmetric it will be.
Actually, in case of asymmetric case means under a saturation, under saturation you can say. So in the saturation region, we know very well. Okay, let us see the 2D structure here. Here. So what will happen in that case? If you can see in the 2D, the under saturation or under asymmetric, here the height will be different, right? And here the height will be different. Means n, the value of n will be different, right? So in that case, the situation will be quite complex. Means we have to just subtract. Let us say the channel is formed here from this. So this region is H, and the total is N. This is total N. So you have to do N. You have to calculate like that. N minus H multiplied by W. So this will be the cross-sectional area. So you don't have to go for that because I'm not going to ask questions based on that. So questions will be based on this only. So let us solve one numericals. So the concept will be more clear. So let us talk. Find the get to channel, get to channel capacitance under three operating regions for the given value of, or for the given parameters, you can say parameters of NMOS transistor. Let us talk about the Epsilon ox, which is equal to 3 point. Can anyone remember the value of silicon? Which I have already mentioned.
So 11.7, I think.
No, this
Or
is for the
silicon.
silicon
Oh, okay.
dioxide, silicon dioxide. This is 3.9.
3.9. Yes, sir.
3.9. Okay. And let us consider L is equal to 2 micrometer and W is equal to 10 micrometer and the oxide thickness which is equal to 100 nanometer. Okay. So we have to find what they have asked to find gate to channel capacitance under 3 operating region, right? So gate to channel, it means that GC, which is equal to, okay, and they have not asked about the parasitic capacitance, right? They have not asked. So we don't have to calculate for that. So here the gate to channel will be gate to source plus gate to drain. So under 3 region, right? So just let us draw the table first, that is cutoff, linear and saturation. And we know for the gate to channel, it means that gate to source plus gate to drain. So सबसे पहले gate to source, gate to drain, and then we will GC. Okay. So what is the formula gate to source? Under cutoff, oh, okay, under cutoff what will be the value?
0.
0. So every all the value will be 0, right? Now linear. So in case of linear, what is the formula? CGA
COX into WL.
COX W into
W.
L divided by 2, if you remember. Because under linear, the channel is symmetric. The length of the channel is uniform. So COX, what is the formula to calculate the COX? F70, F7 ox,
Epsilon upon.
right? By
TOX.
TOX multiplied by W into L multiplied by half. So calculate here. If you have calculator, then you can
So
calculate.
total will be 0.78 into 10 power minus 9.
Minus 9. Okay. So let me calculate here. So it will be half, right? Multiplied by, you have taken the value of, okay, F70 is, what is the value of F70? 8.85 into 10 to the power minus 12, right? Multiplied by F7 ox is 3.9 and TOX is 100 nanometer. And multiplied by area, that is 2 into 10 to the power minus 6, and W is 10, right? 10 into 10 to the power minus 6. So how much you are getting? The value is 3.4515 into 10 to the power minus 15 farad. So it means that 3.4515, you can say femtofarad, you can say. The same value you are getting?
Sir,
Yes.
I think epsilon naught should be 8.85 into 10 to power minus 14.
No, you are not calculating in centimeter.
Okay, okay.
Yes. And you can say it is in meter. then how much you are getting? Same value you are getting, or you are getting different? Yes. So the value will be 3.4515 femtofarad. So under linear, the channel is symmetric. It means that the gate to drain will remain same. So now gate to channel with the simply addition. So you have to multiply it by 2. So you will get 6.903 femtofarad. What about the saturation?
4.602.
So it will be 2 by 3, right? Okay. What about the gate to drain under saturation? Under saturation, 0. Okay, this will be 0, and the value of gate to source will be 2 by 3. So same value you have to apply by the 2 by 3. That is, you will get 4.602 femtofarad. So what will be the value of GC, that is get to channel capacitance in that case? So in this way, I will ask you the questions in the exam to calculate the capacitance. But what will be the change? The change will be like, I may ask you to find out the depletion capacitance. I may ask you to, let us say this is for the silicon, right? Silicon dioxide, exactly, for silicon dioxide. So I may ask you for the different materials. So I have already given the data for the different materials, such as I have given the value for, if you check the lecture number 2 or 3, I guess, then I have given the value for silicon nitride, titanium oxide, like that. So you have to remember, or I will also mention in the exam, you don't need to worry. So similar questions will be asked in the quiz and in the midterm. So any doubt in today's lecture?